All right, we're now looking at applications to force. Much of what we said for velocity vectors is still going to be applicable to force. We can say that if we've got a force vector, essentially the strength of the force is the magnitude of F. Common units for magnitude of a force are pounds or newtons if you're in metric. If we're in the two-dimensional case, we've got a force vector F1 and F2. The direction at which the force is applied would be theta, where theta, again, is the angle with the positive x-axis, and tangent theta would be F2 over F1. If we redraw our little triangle here, F1 is the horizontal component, and F2 is the vertical component, so you can clearly see that tangent relationship. Just like last time, we would be able to write equations for F1 and F2 based on the sine and cosine relationships. We know that cos theta would be F1 over the hypotenuse. The hypotenuse is just the length, magnitude F. And the sine of theta would just be the opposite, F2 over the magnitude of F. And so solving for F1 and F2, we get magnitude F cos theta, and then F2 would be magnitude F sine theta. Again, very much like what we found for the velocity vectors. So in our first example, we have a force applied to an object. Find the magnitude and direction of the force. So I'll start with a sketch. X is 36.54. Y is negative 16.27. So there's F. The magnitude of the force, just the way we always find magnitude. Some of the squares of the components, and then take the square root. And that comes out to just about 40. It's 39.998 something, so I'm going to call that just about 40. We were not given units, but again, this would be newtons, pounds, whatever the force units happen to be. And then as far as the direction, we know that tangent theta is F2 over F1, so negative 16.27 over 36.54. And if I take the inverse tangent of that, still in degree mode, by the way, I get just about negative 24 degrees. In this case, that seems like a reasonable result. If I look at this angle with respect to the positive x-axis, the angle here being negative 24 degrees is perfectly reasonable. So I could leave it like that. Or if I wanted to, this would be south and this would be east. So I could also say 24 degrees south of east. To describe direction on that force. All right, we'll look at a couple more examples. In example 9, a man is parasailing, being towed with force 400 newtons by a rope at a 58-degree angle to the horizontal. Find the components of the force vector. All right, well, I'm going to assume this guy is here in the first quadrant. Here's my little parasailing man. And let's see, we do know that the force is 400 newtons, so that would be the magnitude of that vector. And the angle is 58 degrees to the horizontal, so I'm just going to use my positive x-axis as my horizontal. And I want the components of that force vector. So I'm just going to use F1 cosine theta and F2 sine theta to get sorry, I keep doing that. The magnitude of F is what I want here. Magnitude of F cos theta and the magnitude of F sine theta to get F1 and F2. So in this case, that would be 400 cos 58 degrees and 400 sine 58 degrees, or approximately 211.97 and 339.22. Components of my force vector. All right, in example 10, a pendant lamp weighing 15 pounds is suspended from the ceiling by a chain. Find the force vector, also called the tension vector. Now, part of this, and I just wanted to mention this because it's a call you're going to have to make in some problems, part of the way I choose to write this is going to depend on whether I want to think of myself as being in a 2- or a 3-dimensional situation. This is a simple problem, so we're going to do it both ways. But sometimes, if everything happens within a plane, we may consider up and down to be the vertical axis, in which case I may simply say that this would be a 15-pound force pulling straight down, of course down with the direction of gravity, in which case my force vector would simply be 0, -15. However, if the situation that I'm working in requires that I consider forces in 3 dimensions, then I would want to look at this as a 3-dimensional situation, in which case up would be on the z-axis, and my force vector is still pulling down with a magnitude of 15, would now be 0, 0, -15. Typically in any problem, you'll make that call as to whether you want 2 or 3 dimensions, depending on how many different directions you have forces acting. All right, in example 11, a golf ball is hit with a force of 2,000 pounds at an angle of 60 degrees to the horizontal. If the golfer accurately aimed at the pin, which was 45 degrees northwest of him, find a vector that represents the force at the moment of impact. We do have a 3-dimensional situation here. We have an upward angle to the horizontal, so that's going to be a z direction, as well as northwest, which gives me both an x and a y direction. So I'm going to draw this one 3-dimensionally. All right, north is the positive y-axis, so this would be east, and back here would be west. So I'm going to start in the xy plane, and I'm going to say, first of all, to go 45 degrees northwest, we'd be halfway between north and west right here. So let's see here. With the positive x-axis, which is east, this is 45. This would be 135. So for right now, I don't care about the magnitude of this vector. I'm just going to get the direction right. I'm actually going to give this vector a magnitude of 1 by just using cosine and sine. We'd have cosine 135 and sine 135. And that vector has a magnitude of 1. All right, I now need to angle this 60 degrees to the horizontal. So I'm going to imagine going up at a 60-degree angle. And just like the last three-dimensional problem that we did, I've gone straight up from here. So the sine and the cosine and the sine are still going to be the same for the x and the y. Those haven't changed. But I now need a z value. This z value right here. And since I chose a vector of magnitude 1 in the xy plane, I can see that the tangent of 60 degrees would just be z over 1. In other words, z is the tangent of 60 degrees. So I've now got the direction that I'd like to go. Let's go ahead and get a unit vector in that direction, and then we can give it the appropriate magnitude by multiplying by 2,000. It is a pretty big multiplier, so I'm going to keep a lot of decimal places as I do this. So first of all, my unit vector is this direction vector that we found. Divided by its magnitude. And I'll do a little bit of the arithmetic here. All right, I just plugged all that in the calculator there. And this is what I came out with. Rounded to 5 decimal places, knowing that to get the actual force vector, I'm going to have to multiply this by 2,000. So, multiplying those values by 2,000. Oops. Can't type. I'm getting negative 707.1, which would mean that one will be coming out to positive 707.1. And the last one, 1732.1. And that's the force vector at the moment of impact with the golf ball. All right, so we will pause there and come back for a few more examples in the next video.